This is the start of lecture 3. How to always be right. Isn't that convenient, guys? It'd be nice to always be right. Okay, let's take a stab at it. So the point here is, well, rather, the purpose of this lecture is that I'm going to be showing basic proof techniques. We're not going to go over every single proof technique, but we're going to go over the main ones. So let's start with this is a kind of if you take like a course in philosophy about like logic, or even a math or logic course, you'll see sort of these formal things called arguments. So you'll start with a set of propositions, so just whatever you assume to be true. Okay, they're literally called assumptions. And then what you do every single step is justified with some logical principle. So it looks very dry, it's all shorthand, and eventually you end up with a conclusion. So obviously these like logical arguments are not really nice on the eyes. And so what we do is we dress them up as proofs. Okay. So we have something known as a trivial proof, and it involves our nice friend, the logical implication. So trivial proof is where we have universal instantiation. So we say for all x in A, P of x implies Q. So we're trying to prove this. And it turns out that Q of x is always true. Okay. So in this case, this harkens back to when I talked about when I write an implication, it's a promise, right? And you can challenge me by providing P, or I can just always have Q ready at hand. But now it depends on X, right? So if it turns out X doesn't even matter, Q is just always true, then obviously like it doesn't matter what P is, right? And I think when I first taught this, I had a lot of examples about Obama. So there's still this like vestigial note here, but maybe it doesn't make as much sense anymore. Yeah. So always think of implications like promises. Okay. So here's an example for every person in America. So here's our universal quantifier. If they are Obama, then Obama is not the president. Okay, so this is trivially true. It's trivially true because I don't even have to look at this part. I can just look here, and I know this is always true. Obama is just not the president. So so this is a trivial proof. I just show that Obama is not the president. Okay, here's a more interesting one. Okay, for all x in R, if x is greater than 0, then x squared minus 2x plus 1 is greater than or equal to 0. You do that with backslash GEQ for greater than or equal to. And okay, voila, we do some factorization. So we see that this is just always non-negative because that's how real numbers work. So Q of x is always true. This is always greater than or equal to 0. So this is trivially true. And now we have vacuous proofs, which are basically just all the way around. So this is when P of x is the one that's always false. So you can't ever challenge the implication. And here's a silly example. Okay, so for any set A, the empty set is a subset of A. So if we recall, okay, we're trying to show a subset. We have a universal quantifier. For all x in the empty set, it must be an element of A. And that's what I have here. Good. But yeah, P of x is always false, right? This is always false. There's no elements of the empty set. So this is vacuously true. It's vacuous like a vacuum. There's nothing there. Okay. So this kind of vacuous proof is like obvious because it's empty, but there's like something interesting that it's sometimes not clear that a set is empty, and this is because maybe the way you define the set relies on some important properties, and you say, okay, let's have a set where all these properties are true. And my analysis professor actually gave me a funny story where in academia they were publishing papers about some kind of object, and they're like, wow, this object is really, really good, it does all kinds of things, and then they found out that these objects don't exist. They create a contradiction. So yeah, all of those papers were vacuously true. They were talking about objects which don't exist. Okay. So here's an easier example than something like that. If we have x squared less than 0, then this follows. And obviously, x squared is never less than 0, so this is vacuously true. Okay. Any question about trivial or vacuous proofs? No? Okay, let's continue. Okay, direct proof is like the first kind of actual proof. And this is basically what we did in lecture 2 when we were talking about subsets. So we begin with the premises, right? We do something, and then we reach our conclusion directly. So there's no other really tricks. We're just doing logical manipulation. And the key of doing this is looking at your quantifiers. The structure of your proof always starts from looking at your quantifiers very carefully. So I would recommend when you're starting off with writing proofs, maybe just write it out in shorthand what you're trying to do, and that will give you pointers as to what should happen next in your proof. Okay, so right, so this is a common mistake. Okay, so if I'm proving a statement and now I encounter a universal quantifier. So again, like always, we're going to instantiate a new x. It's going to be part of A, and you can't impose any more restrictions on this. If I do impose any kind of restriction, I lose what's called generality of the universal quantifier, and we're just talking about a completely different statement at this point, and it's not valid. So here's a very silly example. Okay, let's instantiate some x inside of R, but now I say, okay, pick some x in R such that x is greater than 0. So obviously, I've lost generality because I haven't dealt with the case where x is 0 or x is less than 0. So whatever follows from here, it doesn't really mean anything because I'm not talking about this statement anymore. I'm talking about a completely different statement. And so obviously, people are making this exact error where they just add on this random property. What happens usually is that there's sort of a subtle, like, I guess, desire to have the object work a certain way. And so, for example, if you're talking about a graph with n vertices, I might see someone assume somewhere along the way that the graph has n minus 1 edges, and that was kind of what they wanted to prove, and then they do a few more manipulations and get the result, and it's completely wrong because that, you know, you're talking about a very specific kind of graph, whereas you should be talking about a very general kind of graph. You can't put any more restrictions. Okay. So now, when you see an existential quantifier, this is where the actual challenge comes along in the proof. Existential quantifiers are basically asking you a question. Find me some element that has the following property. Or, in less satisfying proofs, prove that at least one such guy has to exist. So these are known as, the latter type here is known as a non-constructive proof. It basically means that you don't know what the actual guy to exist is, but you know that there is one. And these are less satisfying, but I think more egregiously, they tend to lack, I guess, kind of power in terms of explaining why something is true. Because when you're reading a proof, right, your goal is to understand why is the statement true, right? Or you want to extend this. And when you have a non-constructive proof, that really can hinder that process. So you should always prefer constructive proofs. But let's actually show you examples of these things so it's less abstract. Prove for all x and z, there is some y such that x plus y equals 0. Okay, so we saw this statement before in homework 1, probably, yeah. So, okay, I need to prove this. So first I see a for all. Okay, so I instantiate it. There's nothing going on here. And now I see existential. There is some y. So in my proof, I need to go find some y. So this is kind of what I showed last time about, okay, I need to go do some scratch work maybe and go figure out what number works here. So I want this property, so what does that? Well, I just solve for y, and I get minus x. So then when I do my proof, I'm doing it backwards. I give you the answer first, and then I show that it works. So once I'm through all my quantifiers, then I do my logical manipulation, I find it's true, so we're done. Okay, so now let me show an example of a non-constructive proof. And now we're going to finally define something useful and relevant, even and odd integers. Here's the formal definition. So an integer x is even if there exists some integer k such that x is equal to 2 times k. So this should be a very natural definition. And for an odd number, so you could choose to say a number is odd if it's not even, but instead we define it like this. It's odd if there exists some integer k such that x is 2k plus 1. Or it could have been 2k minus 1. It doesn't really matter. Okay. So now we want to prove that for any two consecutive integers, at least one is even. So I guess it's a very small thing to note here. But when we talk about the notion of consecutive integers, note that if we want to talk about this very atomically, then you should maybe define what a consecutive integer or consecutive pair of integers is. But I won't be that pedantic. So anyways, so let's let x and x plus 1 be arbitrary consecutive integers. And, you know, people might try doing this proof by saying let x and y be arbitrary consecutive integers, but it's obviously a little bit easier if you do this once you look at the math. So now we're going to examine what's going to happen here. So if x was even, then obviously one of these two numbers is even, we're done. But if x is odd, then we're going to show that x plus 1 is even. Of course, our intuition tells us that they alternate, so this is fine. And blah, 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 math, and then x plus 1 is even. So I'm done. But the point is that this is non-constructive because I haven't actually told you which of these two is going to be even. I just know that one of them has to be. So if anyone ever gives you two arbitrary integers and you don't know anything about them other than that they're consecutive, then you can't know which one is even. So that's a little weird, but okay, there's a non-constructive proof. So we've only really talked about quantifiers and odd and even numbers, so I'm just going to continue for now. So another proof technique, which can be part of a direct proof, is a proof by cases. So we kind of have these mutually exclusive cases that we split our proof up into, and then we go down each different case and we show that the result must be true no matter which case is the one. Okay, and so obviously we just did a proof by cases. Either x is even or it's not, right? X is even as a proposition. It's either true or false, so we have cases based on that. So so be careful with proof by cases. CS majors are really prone to just trying a lot of proof by cases. So this is obviously more of an issue when you have a lot of variables or something. Like even if you just have multiple variables, just two, and you start going by, okay, if the first one's odd and the second one's even, the first one's odd, the second one's odd, and so on. You know, this gets really complex really quickly, and so you should maybe try to avoid this proof technique if you can. I distinctly remember, we had these like quizzes and analysis, and I remember like I had like 6 different cases, and I was just like jumping between them because I was stuck on like 3 of them, and I just like shat myself and I didn't know like how to do it. And it turns out you just shouldn't use cases in the first place in that proof. If I had just, you know, stopped thinking about cases, just hunkered down and thought a little more creatively, then I would have gotten it. So yeah, just a slight caution for proof by cases. Obviously, in this case, you need proof by cases. I don't really see how else to do it. But so contrapositive proof is a nice thing that you can do sometimes. I don't think. Oh yeah, no. I do have advice for when to use this. And this obviously comes from the contrapositive that we learned in lecture 1, or rather that you learned in homework 1. So instead of proving P implies Q, so basically everything you ever want to prove is going to be some implication. So instead of proving P implies Q, you're going to prove not Q implies not P. Of course, these are logically equivalent, so it doesn't matter which one you do. So yeah, so here's a really nice example for when you kind of have to use it. So so for any integer x, if this quantity is odd, then x has to be even. And so this, you know, might hurt your brain a little bit. Okay, this has to be odd. And then you say, okay, if it's odd, then let's go to our definition of odd numbers. That's the only way forward from here. So then this is equal to 2k plus 1 for some k. And then, right, so you have this. And then this like really sucks. Like what do you do with this? You wouldn't know how to say something about x directly. Maybe you can factor this. I don't know if that'll help you too much. I don't know how to factor it. But instead, if we start from the contrapositive, then we have a much easier time. And so the contrapositive, so I negate this, and I flip the whole thing. So I start with x is odd, so that's simple. So x is odd means we have this. This is a great starting place. And now I just need to show that this is even. And I mean, that's like so much easier because now, okay, I know what x is equal to. So, okay, I just plug in 2k plus 1 everywhere. And then, okay, I do some math off screen. And then I find it's 2 times this. So because this quantity is 2 times a number, then it has to be even. So I'm done, blah, blah, blah. So yeah, you probably are not going to use contrapositive very frequently. And don't like beat a proof into the shape of a contrapositive because you are stuck. But if you find that the conclusion is like a much nicer thing to work with, especially when you negate it, then it might be worthwhile trying a contrapositive out. Okay, any questions about cases or contrapositive or anything before either? No? Okay, brilliant. We're doing great on time. Okay, so now we get into, I guess, maybe a very spicy proof technique. It's called contradiction. I'm sure you guys have seen some form of it at some point. And you basically negate what you want to prove. Okay? You assume that what you want is false, and then you show that this couldn't possibly be the case because you get some kind of contradiction. And so that means that if everything else was sound, then what you started with, your assumption that what you wanted to prove was false, that assumption was wrong, and therefore what you want to prove must be true. So, I mean, try please to not do this. So one problem with doing contradiction is that you basically don't really learn anything usually about the stuff you're talking about when you do a proper proof by contradiction. It just kind of shows you that something is wrong when this isn't true, but it really doesn't convince you why this thing is true. But also, I think like the majority of proof by contradiction that I see at the undergraduate level is actually not really using contradiction. It's just using contrapositive. And if you play around with some variables, you'll see why you can make contradiction like this. You can take this and make it look like contrapositive, but by adding some stuff at the beginning and the end about talking about contradiction. So yeah, just try really hard to avoid it if you can. Okay. Okay, and one of the biggest things I've seen actually in a book this was violated. It was terrible. So if you're starting a proof by contradiction, please say exactly this statement. Assume for the sake of contradiction that, and this exact statement is so common that people actually like abbreviate this as AFCO. Sorry, this is not a C. AFSOC. People just abbreviate it like that. And then they begin their proof, and then it's very clear you're doing contradiction. The reason, of course, this is so important is because if you don't know it's contradiction, then by starting to prove the negation of what you want to prove, it's a little confusing. Air Force Special Operations Command. Yes, that would make sense. Good. Okay, so I will, of course, have to show you proof by contradiction. I wish I could get away without doing so that you just never do proof by contradiction, but I would be doing it injustice, I suppose. So let's start by showing you the rational numbers. So I mentioned this before, of course. Rational numbers are these quotients where numerator and denominator are integers, denominator is non-zero, and the GCD of both of them is 1. And in this proof by contradiction, it's actually very important that the GCD is 1. The contradiction relies on this. So they should have, in particular, no common prime factors. So we're going to prove that square root 2 is irrational. So like the Greeks like had a stroke when they realized this was the case or something. But anyways, so right, so we start with the lemma. So if x squared is even, then so is x. So notice if we flip this around, by the way, if x is even, then x squared is even. This is super obvious, right? Because if x is equal to 2k, then x squared is equal to 4k squared, which is equal to 2 times 2k squared, so it's 2 times an integer, so blah, 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 x squared is even. But I mean, this just fits our intuition. But if we talk about our intuition in terms of this direction, right, it's a little bit less clear, right? So for example, if x squared was like 10, right, then this doesn't really make sense. So we're actually talking about only integers. And then you realize, okay, if you're talking about integers and you're talking only about squares which are even, then you notice something's going on. If you squared something and you got an even number, then there must have been a prime factor of 2 somewhere in the original number, x. And so that's how you got the 2 in the squared version. So now that we have the intuition, we can actually just ignore all of that and just look at the contrapositive instead because that's easier. So again, talking about weird quantities being even or odd is more difficult than this being even or odd. So anyways, suppose x is odd, blah, 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 blah. It turns out x squared is odd because you do some math. Okay, so I'm not going to bore you with the details. Okay, so we have this lemma. So now, so now we begin a proof. Assume for the sake of contradiction that square root 2 is rational. And so, by the way, why do we do this? So we know kind of to use contradiction here. Our hint is that talking about square root 2 being irrational is difficult because we're saying there are no such p and q such that p over q is equal to root 2. So that's like a very hard thing to talk about, being irrational. Being rational is a lot easier because now you actually have p over q to work with. So anyways, I say, okay, suppose root 2 is rational, then you have this, just from the definition of q. Okay. And so when I say coprime, that just means their GC is 1, just some number theory terminology. Okay, so now I do some math. So, okay, root 2 is equal to p over q, so p squared over q squared is 2. I just square both sides. And then I move some stuff around. P squared is equal to 2q squared. Nothing crazy going along. But this does mean that p squared is even. Okay, so now I use my lemma. That means that p is even. Okay, so p is even. So that's sort of some big information. So if root 2 is equal to p over q, then p has to be even. Okay, but now if p is even, we have this, right? P is equal to 2k for some k. And then I do more math after substituting that in. And it turns out that q is also even. So now something's wrong, right? P is even and q is even. But p and q are not supposed to share any common prime factors. And that's the contradiction. So you're probably thinking, like, what just happened? Why does that have anything to do with square root 2 being irrational, right? I just showed that something weird goes along with the numerator and denominator, and I mean that's the problem with contradiction. You've kind of unfortunately missed out on the logic or any kind of fundamental reason as to why you can't have this number be rational. And if you sit and you think, and you try to generalize this, for example, okay, what if I talked about root 3, right? Does anyone actually want to take a stab at how to show that square root 3 is irrational? I'll give you a minute to think. So don't worry about like very precise details. Try to understand why or rather how much of this proof we can maybe reuse for square root 3. Oh, we have a hand raised. Go ahead, Henry.
Okay, so let root 3 equal p over q.
Okay.
Then square both sides, so you get 3 is equal to p squared over q squared.
So let's just do okay, so p squared q squared is 3.
But the contradiction, or well, when you multiply both sides by q squared, you get p squared is equal to 3 times q squared.
Sure.
But q squared has to have like each factor has to be to an even power. But when you multiply by 3, it will create odd power, and p
Good.
squared cannot be odd power.
Good, good, good. So that's the intuition. Very good. So what Henry is saying is that okay, um, look at the prime numbers that appear in the factorization of q, right? So these prime numbers appear with some multiplicity. When you square it, all of those multiplicities become even. Same thing on this side. But now we have this extra guy, 3, just sitting around, right? And that means that the multiplicity of 3 on this side is odd, and the multiplicity of 3 on this side is even. And so that's the intuition, and that's very good that you found that. And probably the easier way to do this, in terms of actually making this rigorous, and yeah, obviously, you probably understand this, but going from intuition to rigor can actually be very, very challenging sometimes. So my advice for doing that would be roughly to rewrite this lemma to work for the number 3. So in this case, it would be if x squared is divisible by 3, then x is divisible by 3 as well. Okay, and now we note that we're not using even or odd anymore, we're just using the number 3. And what's special about 3? Okay, it's prime. So I can replace 3 here with any prime number, so let's just call it a, and then what Henry said is still true. Okay, so when is the square root of a number actually, rational? And that happens precisely when you don't have that problem of multiplicities. And so that means that every prime factor of that in the number you're taking the square root of must appear with even multiplicity. And so the point isn't to go into all of this, stuff about primes and whatnot. The point is that I've said something very important about square root numbers and their rationality, and that appeared absolutely nowhere in this proof by contradiction. And that is kind of the loss I'm talking about when we do contradiction. Okay, I hope I illustrated the point. Any questions? Oh, okay, let's continue. Oh, there's no continuation. Okay, wow, we're already at the end. Quite a fast lecture. Let me skim over the homework here. Right, so just these are going to be either vacuous or trivial proofs. Yep, some basic direct proofs. Yeah, so maybe you're using contrapositive here. Here maybe you're using proof by cases. Okay, so I will say, if you don't want to do 5, just don't do 5, because this is a really shitty problem. Originally, this problem wasn't on the homework, but last year the guy who was lecturing, really had a thing for this stuff, and I don't. So feel free to just ignore it. I think it's not very instructive. So yeah, really just focus on 1 through 4. It is a good number of proofs, so start early. Say 1, 2, 5, 7, 11. Yeah. So it's 11 proofs. Start early. Make sure you have time to make sure that everything makes sense. And yeah, have fun, guys. Any questions? No? Okay, all right. Thanks everyone for coming. Take care.